can measure the mean diameter. How to measure the mean diameter? It's a simple arithmetic mean of all the different dimensions A, B, C, D. So tell me, how can you find the arithmetic mean? It's arithmetic means total numbers, total amount divided by total number, right? So then this is the first way to measure the dimension or a size of any sediments. Then some people also use the nominal diameter. So nominal diameter is the diameter is a diameter of a sphere with the same volume of these particles. So you can see we have like, you don't have to, if you don't understand the definition, then you can use simple this formula. We have the A, B, C, D. These are different dimension of these particles, and 1 by 3 that can give us the nominal diameters. Then sometime we also have to do the sieve diameter. Sieve diameter is just a square size, which is 0.9 multiplied by nominal diameter. So this diameter. So this moment might be why, but slowly when you move to the next level, understanding the mechanisms of the sediment transport and all, these diameters are very important. So now we are able to know the dimension of any single particles, right? So tell me, if I give you the different size of the sediments, can you try to find the mean diameter? How many of you can come up with the mean diameter? Anybody? So if it's okay, I understand some people always be shy to talk with. So no need to be shy. Try to be strong enough. Nothing is wrong, you know. Whenever I write any questions, I will try to answer. It's none of the questions is wrong. So always ask questions. So anyway, so let's move this table I just give you. So when whatever the size dimension that you measure and calculate, so we have the different range, right? So if the size range lies between this area is known as boulder and the cables. Then once the size is lies between in this range, then we can also that's size of the particles are known as gravels. Okay. This all the data you can go. I will share the slides later after this talk, so you can go with in a detail. Then for the sand, the size is if less than 2 mm are known as generally the sands particles. The silt are less than 0.62 mm. So this is in these columns are given in mm. These columns are given in inch. This is also in a mm, but in a different. It's easy to remember if you compare the different classes: coarse sands, medium sands, fine sands. But this value sometimes people difficult to remember the point system. So it's very easy. You can remember. So 1 to 2 mm, then 1 to 1 and 1 by 2. Then it's just divided by 2 everywhere. You can go up to the last. So this is just a division of 2. So it's easy to remember. But if you don't have to remember, generally in the normal case, when you research, we always get data. So you don't have to remember the specific size, but just remember the sand size and silt size and clay size range. We just have to remember the range from 2 to 0.062 are from here to here are the range of the sand particles. Okay, so now you know the different particles. Now here we have the questions for all of you to solve. So here I have given you 3 different particles, right? Particles P1, P particles 1, particles 2, particles 3. And now I show you how we measure the dimensions. So I have helped all of you guys to measure the dimensions. So we have A, B, C, means 3 dimensions of each different particles. What we have to do, here we have to calculate the mean diameters, as I have discussed earlier. Then we have to calculate the nominal diameter and sieve diameters. Then we classify the different classes. So here I have given you the formulas. So anybody can help me to find one. Calculate the mean diameter of this. Anybody help me? What is the mean diameter of the particle 1? Do you guys need some time?
Come on, guys. If you know, just respond for Professor Kumar.
Yeah. Anybody
Maybe you
willing
can
to?
choose also the chat box. if you try to pop on the
Okay,
question.
so if nobody willing to answer here now, but we can take it as a homework. So maybe next class we can come up with the answer and you can share with your supervisor and professor in your classroom. It's also fine. You don't have to come to me. So this will be the homework. I think it will be very easy to calculate. I have mentioned the formula. Just put the formula, the value here. You can come up with mean dimension, diameter, and then you can put the nominal diameter here. Use just all value and calculate using the calculator. You can come up with then shift diameter. Then this questions number 4 we can classify. So once we calculate the all diameters, then we can compare with nominal diameter with the table I shared before. Then we can classify the different category. We can come up with which category is what, and then try to find which diameter is the largest one, which one is the smallest one. Then try to understand which can settle down faster. Maybe this one we need answer to understand, but this is your homework to answer and then understand the play with the Googles and ask your supervisor and professors who will be like settle faster. And then last diameter, last one is very easy. You can understand why the mean diameter and nominal diameters are the different for the same particles. We try to come up with the answer in the next class. So now in reality, generally we don't have the single sediment. We have the bulk of the sediment. So we can see the examples here. So that's why we have to understand the total distributions. If I ask you what is the general size or mean size of this whole sediment particle, sediment size, sediment sample, none of you are able to answer because you only know how to measure the single particles. So we need to do the distribution. So for doing the distribution of the size, have the different methods. We have the flow resistance methods in transport and laboratory shifts analysis. These are very common. I think you may have to study in your bachelor degree to understand the size distribution of the sediment sample. And then for the large size, we can also count, So here, if I ask you to count the number of the large sediment particles, so like this one, 2, 3, 4, 5, 6, we can count it, right? So anything is more than 60 we can count it manually, but AI is coming, so AI can also help us to count. But for the fine sediments, we need the different methods. Pipette methods also available, but I generally use every time I use a laboratory sieve analysis because it's very easy and very standard method to understand the size distribution. So why do we need size distribution? After the size distribution, we can come up with a single mean diameter of all the particle size. So you can see here how the sieve analysis work. So you can see the larger area can retain over the per sieve. This is just a collection of the different size of the sieve. Sieve 2, 3, 4, 5, 6, 7. So now we can see the larger particle can retain over the first the sieves, and the smaller particle can pass through this, right? So by doing this, then we can create the percentage of each of the sediment size here, and then you can plot this diagram, cumulative. This is percentage finer. Percentage finer means what is the amount of materials can pass through the first. So means this shifts the most of the materials will pass, only this material will be retained on the top, right? So so if you add all of the materials, suppose it's a 10 kg materials samples, then 5 kg only retain here. So percentage final means 1 kg retain here. So percentage final means 9 kg. This 9 kg just pass through this one. So 9 divided by 10, that will give the percentage final. So if you do the percentage final, you can get the plot like this. So in the x-axis, you can see is sediment size. Sediment means sediment diameter. Sediment diameter means we can measure the diameter of this one. So this diameter means the actually this is the size of the sieve. The size of the sieve is here. So because it's everything is retained because of based on this size. So that's how we can consider, okay, size of this particle is more than what you measure mentioned here. That's why it's not passing through the sieve. So that's how we calculate the passing percentage finer. So then we do the percentage finer. Why do we need to do this? Because we have to come up with the sample size of the sample total. So now here you can see there is a concept called D50 means a diameter of 9.5 mm. Nanometer, sorry. What does it mean? So you can see the 9 diameter means there was a sieve. The 50% now we have the 10 kg of materials. So the half means 50 kg, 5 kg of materials pass through that diameter of 9.5 mm sieves. That's meaning is this simple. So why do we need? Similarly, we have the D90, D75. D75 means 75% of the material pass. So by doing this, we can come up with the geometric mean. So geometric means help us to understand. This is a formula. You may not have to understand do the every time, but I think it's good to understand the what's a mean diameter of overall sample. And then you can also come up with the similar size and the mix size. You can know, right? All particles are on the same size. So how can you tell it? For doing that, we have the sorting coefficients. This is just ratio of D75 and D25. If the ratio is very low, that means well mixed, means all of the particle size are the similar. But if it's very high, that means all the particles have the different size of materials in this sample. Is it clear? So now we have to understand how the sediment process, sediments form, we understand the sedimentation process with weathering, erosions, transportation, and deposition. As I said, four different mechanisms. Here, weathering means detaching the sediment particles. Yeah, one
It's
questions.
me, Tono. So I just maybe the student don't know about what the function, why we need to measure the grain size.
Yeah,
Yes.
they know, right?
Yeah. Why we need to measure the particle size?
So
To
they want to know this answer.
yeah, yeah. Maybe you can share.
Yeah.
I also want to know actually, and maybe you can share the question. And
So So now we know you measure the size and understanding, right? So now here is the understanding the size of the material is very important here. So now here you can tell us size have variable. Okay, I will discuss each of each of the process. So weathering can also help, like we can know either the materials will be easily eroded or not, also based on the size, and what will be the how it will transport from one upstream to the down is also depends on the size of the materials. So if size is, that means it can suspend in a water and then it can go with the water. But if size is too large, means sand and gravels, that only always go with the river bed. It cannot go to the suspension. That's why size is very important when you try to understand and try to model the sediment transport. So now here we have one schematic diagram for understanding the erosions and then depositions and also transport. You can see in upstream river basins always have the source of the sediments, right? And then this the plain, the floodplain area and the low elevation zones are the transportation zone, and then also this the deposition zone. But most of the sediments are deposited in this delta regions, right? So so this overall process is seems like the conveyor belt. It's a start from erosion from the mountain area, and then it takes all sediments, and the sediments are start being transported and deposited in the delta regions. It's just continuous process. But this here on conveyor belt is happening because of the conveyor belts, but in the reality, it's happening because of the gravity, and the gravity means it's a change in slope. If there will be no slope, change in slope means there no most of the materials will deposited in that place. So this type of situation we generally find in the delta region. How many of you know the delta? What is delta? Anybody? How many of you have seen the delta in your life?
We have one big delta in Borneo actually.
Oh, Borneo. Oh, very
Some
nice.
delta, yeah.
Okay, so I think everybody have seen the delta in their life almost, right? So deltas are formed because of the deposition of a lot of sediments. So whenever sediments come to the delta part, so size is very small because it can transport to the long distance, right? That's why we need to measure the size, especially for modeling the process. There are many, I cannot tell all of them today in a short lectures, but there's many we also learn why need to measure. Sometimes it depends on the purpose. Sometimes people try to measure the size to understand the erosions and the erosion, like how to say, like understanding the materials quality itself. So is it abrasive materials or something like this? It's easy to erode or easy to like so like its size also tells many geology and the paleoclimates people can come up with. So that's not my background. So here my background is to understand the size to understand the transport process. So how many of you know the point bar? You know point bar. I think in Malaysia or in Indonesia have a lot of point bar. Point bar is this bar, you know. So when the river start moving and then it start eroding this side, so the river will start moving this side and start depositing in another side and form the point bar. So it's a point bar is the collection of lot of sand and the sand particles on the another side. Similarly, you can see. So now here we have the different factors that affect the sedimentation process and sediment erosions and then all the particles, the climates, then we have the rock properties means the different type of rocks and their chemical composition, size. Well, topography will help us to understand what will be the flow of due to the slope changes. Then vegetations, vegetation is very important. It's a nature-based solution. People they use a lot of plant on the river bank to protect the river bank, right? And then we have the river land management is agricultural practices. So we can use the different agricultural practices in real life to reduce the erosions from the river watershed basin. Then this all combine mostly in two factors, erosivity and erodibility. So I will discuss these two terms in a later that is decide that how much the sediment will be detached and move from one place to the another place. These two factors are very important that I will be discussing along with the slope and other factors. So as I mentioned, the climate is the major factors that affect the soil loss. So, for examples, we have the precipitation as well as the temperature, wind, and solar radiation, evapotranspirations. But many of people alive they consider precipitation for the soil loss equations that directly help to detach the sediments from the river surface. I will be discussing in a later. So here we have the global rainfall erosivity map. Erosivity map are mostly made based on the rainfall data. So here you can see the total annual rainfall happening. So this area we can see the what though this area have the I think the millimeter. Yeah, this area we have the low amount happening in these regions, but yeah. So, and this one, we can see the lowest amount is African country have the lowest amount of the rainfall in this region. So we can see the similarly, we also have the R factor, means these regions we have the less amount of this less R factor means the is a less energy that can erode the sediments from the land surfaces. So totally depends on the rain. First is like rainfall is help to detach the particles. I will be discussing in the next slides much better understand the other factors how climate will affect the work. Climate also have the temperature, temperature. If increase the temperature, is increase the biological reactions. Biological reactions means once the more biological reactions that can they can eat the food and faster and eat the soil and then can erode the materials. So let's watch the one videos how it was very short videos. We can see we are increasing the this part, and you can see the biological reactions and start eating and try to decompose the soil, decompose these leaves. Here another side we are not increasing the temperature, so there this process will be much slower than the can have the very great look. So that's how here the main motive of showing is to understand the different factors that can come up with the can affect the climate is the one factor. So temperatures and the rainfall directly related to detaching the sand. So now we have the erodibility. So erodibility is just is it's about the susceptibility of weathering. So this is related to the property of the sand sediment particle. So now we can see the fine textures. That means fine textures soils are easy to erode. It can be eroded very well and deposited in somewhere. But here you can see the bedrocks. Bedrock is quite hard to detect, hard to erode these materials. For this eroding this one, we require a huge amount of energy from the river water that can be not eroded very easily. So you can see these materials can eroded very easily, but these bedrocks are not easy to erode. So this like erodibility generally help to measure how our soil resistance to not detach materials from their surfaces. So that's how the erodibility terms are. So another factor is also controlled by erodibility that is also control the slope. The slope, you can see the topography. Then we have in the upstream. It means here is here to here you can calculate the slope. I'm not sure how many of you know how to calculate the slope. Is a slope is a change in elevation divided by total so create the happen on the mountain regions. So now can anybody tell me what is the patterns of the drainage pattern? Here you can see this all happens due to the rainfall. So you can see the most of the rainfall happen on the upstream and then it's start flowing through the downstream. Like not downstream is a depressed area. So these are the patterns, right? So we may able to find later what the gully formation. I will tell you later. The slope profile also here. I just put it here because I think this one is very like we need to have interaction for understanding this overall process. So we can, but here I can show you that these are the secondary forest and then erosion landslide happening here in these regions because these have very high slope, right? On the high slope area have the high rate of erosions and high velocity of the movement from up to down. So these regions have the very high um, erosion. So in these regions always have some disturbance in the soil movement, right? So these regions we cannot find the in situ condition of any sediments, but in these regions we can find the in situ. And then in this region we also we cannot find because this always have deposition these regions from the upstream to downstreams. That's how the work. So we really have to understand the process, the geographic process, and then to tell where the sediment coming from, then we have to understand the in situ conditions. So even you get this size and we can see the roundness, we can tell the many different process. So that's will detail today. So now, as I earlier I mentioned that we have the different process like fluvial, then we have the agent of water and river, the flood that bring all the things. Deposit are also known as alluvials, and then locations are always happen this one in a valley and floodplain area. Then we have the mass wasting. Then terms I won't give because of the gravity. So this happen on the slope and the foothill slope, foothill. So now we have the agent, which is Hawaiian. That's movement of the sediments are known as this. This happen generally in desert and coastal area. Then glacial as well. So this just a summary for different agents and different process, geomorphological process and transport process are named for the different agents differently. But overall, it's just moving the sediments, right? Now we can discuss the rainfall factors. Means climate factor is affecting the sedimentation, sediment erosions. Sorry, and then we have the erodibility, means the property of the sediment uh, itself. If very strong, like detach, like if they have the strong bonding force, means difficult to detach. So now we have the land management. Land management means how can you manage the land in a proper way to reduce the soil erosions. So impact of deforestation. So now if you do a lot of deforestations in the life, then it will decrease the binding force on the soil. So like there is no more binding force coming from the root of the different trees can create the easy for rainfall to erode the materials from the surface, right? Then we also have the global warming and flooding. So that means the more global warming, more flooding, global warming can increase the biological rate, right? As I saw the videos, that can also increase and alter the soil erosion rate. So we can also go to home and see how the land managements are very important. So this type of things we have to, so we can see here the landslides, a lot of landslide happening, and finally it will lead to the lot of sediment erosions and go to the river movement, river bed. So of course, many people have understand what are the impact of the agriculture expansion on the floodplain sediment budget in the Mekong River Delta is published by my professors, and you can look at what are the different impacts. Like people are changing the agriculture activity and the agricultural patterns to reduce the erosions. It's very interesting, and then we can also study this later. So now we finally go to, now we understand overall how it's work and how the soil erosions happen. So now here you can start with real mechanisms and try to come up with how the river start forming, right? So I start with the rainfall drops. Even we have the small drops of the rainfall start creating the detachment of the sediment particle from the river for the land surface. That is known as erosivity. Then we have then usability is a function of kinetic energy, kinetic energy of rainfall. So how it's work is like, oh, like it's anybody anything we drop the materials from the high level, then it start increasing the velocity, right? The similar concept. So when water drop from the cloud, then this gain the velocity, reduce the potential, gain the velocity. So based on the velocity, we can calculate the kinetic energy. How to calculate the kinetic energy of the rainfall? Kinetic energy of the rainfall totally depends intensity of the rainfall. Intensity of the rainfall is amount of the rainfall divided by time. So for examples, 10 mm of rainfall happen in a 1 hour, so means intensity is 10 mm per hour, right? So high intense rainfall can create more erosions. Low intense rainfall cannot create huge erosions. Then we have the property of the, this one we can also call it as a erodibility over the land, and then this one is a property of the soil. So it's like, as I mentioned earlier, even the huge amount of rainfall happening, high intense rainfall happening, but if soil property is something like the stones cannot erode the materials, it can only erode the materials on the very fine particles, sand materials, and all. So understanding the different type of sites is very important, that you can decide the what type of sediments are it is and how it will be how, like, what is the risks of detaching, like, so detaching of that materials. So we'll go to in another sections later very soon, that you can see the how the sites is very impacting to the sediment generation. Means some a small area a large amount of the sediments that we can come up with the site, if you know. Then, so is the process I start with the detach. Detachment means you just moving the sediment, sand or any particles, sediment particles from the main origin source, means the land surface. This is detach. This is always happen with a splash water, a splash rainfall. So you can see how the splash rainfall. So you can see this, the even the raindrop, right? Raindrop happen here, and then you can raindrop also happen in the some amount of the waters. This is these are known as actually the splash run, splash rain. Then is we can see a start here, being dropping surface while colliding with the land surface is a start a splashing. A splashing means it's detaching the sediment particles from here. So you can see the white one is a drop of the water, but the black colors you can see some materials. This black color is materials along with the waters. It's detaching from the surface, right? Then it start moving to another place. This start moving. So this transportation will not understand. And let's focus this create the movement from here, and then we deposit somewhere. So the materials from here it deposit to another place due to the due to the rainfall, right? The high intense rainfall. So but in some case, if rainfall is not very heavy, means not very intense, so it cannot create a detachment process. So the first factor is rainfall that create the detachment for the soil loss. It's a start from the rainfall itself. So now we can see in the real, but here you can also see the splash rainfall in the real life. So we see due to the rainfall is a small depression. We can no movement, but there will be some. It will be detached here, and we can see here and fall here, and then some materials here are detached, right? So this type of materials are easy to detach. But if rainfall happen on the very hard rock surface, there will no much like detachment. So in the sandy sand materials are very easy to detach. So you can see the detachment here. The all materials from here are moved to another place, spread around the uh, area. But in real life, it can be a smaller, it can be bigger as well. So if rainfall is continue, then it's a start forming the seat of the water. Means the we can see we might have also seen in your life like we rainfall start. Then no moment a lot, just the accumulation of the water on the land surface. Those are the actually the known as the seat wash. It's just a movement. It's not create anything. Not enough time for infiltration and evapotranspiration. Means not enough time to push all the water inside the river, inside the land surface. So this can only accumulate on the over the it's just a thin layer of water over the surface. Those are known as the sheet wash, and sometimes it create the sheet erosion. So in you can also see in real life, because in Indonesia have a lot of rainfall happening in real life. The water sheets look like this. So at this moment, the then is I start moving slowly based on the a small movement. So you can see it's a very uniform movement. It's not something very overload, overland. It's like iterated and a very huge flow, because the seat is just a seat over the land, and you start moving slowly, slowly. But due to the velocity, due to the slope and different locations and the shear stress, it's a start forming. Maybe we can have yeah, it's a start forming. So here you can also see this is the one examples we have taken here. So you can these are the sheets, water sheet on the regions. So is all the seeds are uniform, then is come up with increase the concentration and try to concentrate all the water at the same small locations, so that will form the reel. So reel means it's little bit deeper than is flow down and flow down, and then it's become increase the shear stress can concentrate the flow. Means its overall concept here is to all the water that narrow points and start forming the reels. So this one, if we should have some minimum slope to form this, so this can start moving from one to another. Here we don't have to have any slope, it's just a sheet of the water on the earth surface. And then we have to have some slope, so it can create the um, concentration of flow and start forming the small reels. So reels are usually less than 10 centimeter in a width. So it's the width of the small, like width means the one bank to another bank of the reels are not more than 10 centimeters, that all the reels. So now when the many reels, you might have seen the small reels in your in agricultural land. So when the rainfall happen, is create the small channel here. This also this one you can call it as a master reels, but here you can see the water from this sheet land surface area will come to join here. So this will create the one reels. You can see many. Here is the one NTU campus. You can see there these areas are the. Sorry, it should be. Yeah. So you can see this. Here we are start creating the reels, and then these are the splash sheet over the land surface. And in the long period, this has start making the gully. So here you can able to identify the different reels. So you can see the channel type of structures are known as reels, and it's only happening because this slope is a slopey land, means it's a high elevation, and the low elevations land. Then on the top we can see that there is no much slope, almost uniform slope, so there is no movement. Those are known as a sheet flow. Then combine, here you can see a lot of small reels are combining and master reels here. Then master reels, then many master reels concentrated and form the gully. So it's like a start from the sheet erosion to a small reel, and reel form the gully erosion. So gully erosion is happening on the large scale. You can see here, it's very big and large compared to the real erosions. So this can, this their width can be more than several meter length. Width means this width can be more than several meters, not under the 10 centimeter that for the reels, right? So this one slope should be much higher compared to the real one. So it should have the mm, like I start continuing the lot of water and sediments together along with the lower down the downstream, means the low in a low elevation area. So here now gully is generally like the rivers, but misunderstanding. So, but all the gullies are not always produce the rivers. You know, the gullies structure are seem like the dry rivers. How many of you have seen the dry river in your life? If the dry river means generally we have the water during the rainy season, but in during the dry season we don't have the water. So those type of rivers are mostly a small rivers and can be considered as a gully. So for gully become the rivers, we should have few conditions. The first condition is that there should be the incision maintained and enlarged through the continuous erosion process. It's not means there should be sometime erosions and there time no erosions, and there should be always sufficient water resources to drainage in a sufficient area. So if not sufficient water, that means during the dry period when no rainfall, there no waters. That means that cannot be counted as a river. Then it should also have the deep enough, means the river, the gully should deep enough to water tables are the permanent water, groundwater, right? Once our gully touch the permanent water is considered as the river. Here you can see in this the groundwater is much lower than the this gully, so this cannot be counted as the river. So now here we have the perfect examples of all of the different erosions happening from the different processes. So it's starting with the, let's zoom into this part, and then you can see this the ridge line, that's overflow here. Overland flow means it's a sheet flow, and then it's start forming the small reels here, right? Or small reels merge to the master reels. Then master reels merge to all the gullies. Gullies means main line, main stream. Then after the gully merge to the main stream together. So streams I differentiate between gully and streams, right? Streams means river flow, and the gully means the flow during the rainfall is only because of the rainfall, not because of the groundwater contribution. So these whole areas are known as a drainage area. Why this drainage area? Because if you consider this is the outlet of river basin, so if you try to measure the sediment discharge and sediment load and sediment water volume here, this all water will come and contribute to this point. Located at higher elevation means the highest elevation of the zone, highest elevation of the land surface. So you can see here, so some of the water will flow this side and this side, so it's here, right? So this line are always known as ridge line. Then what is valley? Valley is the low elevation line, right? So valleys are always this low elevation. The high elevations are known as ridge, and that can differentiate between where the water will flow. So now here we have yeah, now here we have different loads, right? As I mentioned, now all the sediment erosions from the land surface and come up to the stream. The river means river flow. So now we have to understand the what's a sediment load, what is the sediment yield, and what the sediment and delivery ratio. So sediment load means total load, means total amount of the sediments passing through the cross sections, measured through the mass per unit time. Means generally it's a huge amount of the sediments, so we can also measure in a kg per second, but generally for the sediment it's a large amount, so we need to have the larger unit. So ton per year is very common in real life, but this can be any unit. We can have the kg per second or kg per unit depends on science to person. So now sediment load here means how much amount sediment passing through this cross section. That's called load. It's just a unit. There, how much sediments is passing, because all of the erosions happen due to the rainfall. It will not come up to here. It will only is some amount of the sediments from the upstream. It will reach to the outlet of the river basin, right? Some of them it can deposit it in on a nearby. It totally depends on the local conditions. So now the next term is to understand. I said sediment yield is the total production of the sediment per unit area. So for examples, we have the outlet of basin here and here, right? We have the same amount of the sediment load. We got that much sediment load and this much sediment load for the two different river basin and main outlet. So 6 million ton per year outlet. We have the sediment load and 6 million. Both have the same amount of the sediment load. But problem here, we can see the interesting thing to understand. The one have the Santa Clara have the highest area, means drainage area that I mentioned here, the drainage areas. These are whole drainage area. So one drainage area, but both have the 6 million tons per year. So what's happening here? So if you try to calculate the sediment yield, then sediment yield is it's a definition here. It's a definition is production of sediments per unit area, right? So we have the load and you divide by total area, then it's become the per unit area. So we have the 6 million and divided by this, then one kilo. Then you divide, then you get this one value, right? So this is 6 million, and then we have the area is this one. So if you divide 6 million ton per year divided by 400, 4,200 kilometer square area, then you will get the sediment yield. So you can see that this basin have the higher sediment yield compared to this. Only because this has the low area, right? Low area and same amount produce the higher sediment yield. That means this a small, although the area is a small, but the amount of the creation, amount of generation of sediments are much more higher than another. So this can be due to the many regions. Maybe these regions have less forest, these have more forest, most different type of the sand material, like different type of sediment materials, maybe hard rocks, and it's not easy to erode. Maybe these regions have less rainfall, these regions have high rainfall, that's creating the high amount of the sediment, right? And then we have the sediment delivery ratio. So sediment delivery ratio is just a sediment load between upstream to the downstreams. Means if you have two, one plus, you can see the how much sediments are delivered from here to here. Means some amount of the sediment deposited, maybe some. So that's how the sediment delivery ratio calculate. Maybe we able to come up with some answers for the larger. So I have the one exercise for all of you to calculate. So we have the two river basin, Columbia River Basin, Wild Basins, both are adjacent. And then I think I have answered all of you that we have basin, and then one area is a 5,000 kilometer square area. Another wild basin has 1,000 square kilometer area. And then we have the respective load. Here we have the 5 million tons per year. So this is a sediment load, right? Now your job is to calculate what is the sediment yield for both basin, right? Possible reason why one river basin have the higher sediment yield compared to the another. All right. To now, this is our last slides, since I think we didn't do um, the classwork. So I think we have enough time, so I can show you here, and then maybe we can discuss after this class. Then what we'll learn? We'll learn where the sediment originate, right? Generally originate from the mountain areas and the high slope areas, and it start due to the weathering and erosion process. Study the erosion process due to the rainfall and also the climate. Just a brief understanding how climates and the biological erosions. So there's a many different method of erosions. So this will you will study in the soil mechanics or some other weathering process uh, courses. So here we mostly focus on the physical erosions due to the rainfall and then other different process, the ice and wind and all. Then we understand this how the particle size control the transport behavior. There in the detail we can understand, but here I have given you the only the proper understanding, the overall surface understanding of the particle size and why that's important. Then how the climate and slope, this all the climate and topography means a slope also always affect the movement soil, right? and then forests and deforestations can also cause the high rate of erosions, and that can finally leads to the high sediment yield. Then we also understand the overall process and the starting of a river from a start from the splash, and then a splash erosion, and then we start accumulating the all water, and from the air, thin sheet of the water start moving slowly and concentrated due to the small little slope, local slope, and it's merged together because of the large because of the large bodies, rivers, streams, if they have discussed earlier. Then we would try to understand the different yield and the load. What's the difference between sediment load and sediment yield? Anybody can answer me? If not, then why this is important? Because if you understand, if you know the yield and load, we can differentiate the basin behaviors, right? Which basin creating the high amount of the sediments is totally depends on the sediment yield. So this can give a quite understanding. Although we don't, if you don't go to the field, we can still know there's a many regions, right? There can be possible regions, and this all very important understanding the sediment process. So next class I will see that I will show you how the sediment move in the river and how people do the modeling and different techniques and methods to measure the sediment transport process. But I will give the lecture on that, but I will share the how to estimate the soil loss equations from the GIS. So I have created a Python GE course, Google Earth Engine course, and a stepwise guideline. I can share that PDF with all of you. So in the end of your master, like end of your bachelor and everywhere, if you have any class project, you will able to estimate the soil loss equations from the Google Earth Engines. So I will share that one, but I will not go with the detail, like it's a totally technicals. I don't like to do, but if you have any questions on that, I can help you. So, but next class I will teach you the sediment process. So now you have understand almost the sediment load, right? How the sediment load move from one to the another place, and how we measure it in a real life. So that's I will talk in the next class. Now I would like to learn from you, like what the all impacts, what's all the questions I have given to you, and the questions I put in the slides. I will send the slides after this talk. So please come up with your, and if you have any questions, please feel free to ask me. Thank you very much.
Okay, thank you very much, Dr. Sunu. Okay, Pak Aditya, you can.
Yeah, well, thank you, Wafid. Thank you, Prof. Kumar. So, just wondering, I'm not good in sedimentation or
Yeah,
sedimentology. So the basic concept is all material that turn into the grain shape of sand, we call as
yeah,
sand.
yeah, yeah.
Is it correct?
No, no.
Okay.
Can
Wherever
you
they
type
come
it?
from.
Because I cannot hear your voice very clearly because I can see the echoes and
Okay. Okay. Can
yeah,
you hear me
I
now?
can hear you.
Okay. So this is about the terminology of
Yeah,
sand. So we classify the material
yeah.
as a sand is only from the type.
Yeah, okay. So as I understand your questions, you are saying that when you classify the materials, it's a sand or clay or anything, right?
That's what I mean is, if the material come from volcanic
Oh,
activity.
okay, I got it. No, it can be anything. It totally depends on the erosions. It's like the movement. So if it's the same materials is coming from large distance, so this can create when there is erosion happen due to the any physical process, it can create the sand, clay as well as the silt, and so it totally depends, and it's a start moving for long distance, and their size become smaller and smaller because of the continuous erosions and every, like how to say, is a friction between two different particles also reduce.
Okay, got it. Thank you.
But ice generally, the volcanic ice always generally generate the sand, a lot of sand in Indonesia. And many
Yes,
people are using it, right? Yeah.
yes, correct. We have a good quality of volcanic sands in even in our city. Yeah,
Yeah, yeah.
yeah. Thank you, Professor.
Thank you very much. Yeah, I am sorry because I don't know how to do the online. I like to do the interactive talk, right?
Yeah, that's okay. That's
I
okay.
like,
That's really good for
yeah.
my.
So I cannot monitor them what happening. They are really understanding or not. So
Yeah,
it's like this. Yeah,
thank you, Professor. I come back to Pak.
yeah.
Okay, thank you, Pak Adit. Maybe any question from another participant?
So if not, then maybe we can see the answer from your student that I have given assigned the work for them to do the homework, and then I will share with you the word file for understanding the Google Earth engine how to do the soil loss estimation, and I will a little bit briefly go through the soil loss estimation equation next class, and then we can do by your own. So is it okay now I leave, or if you don't have any questions?
Yeah, it's totally okay, but please don't forget to share your material